video presents a paper entitled Applying Model-Based Systems Engineering to the Development of a Test and Evaluation Tool for Unmanned Autonomous Systems and is intended for IEEE Systems Conference 2020 audiences. Please note that it is narrated using text-to-speech software. The authors of the paper are Dr. Solomon Gebrehyanis, Dr. Ali Karamadini, and Dr. Abdullah Homayafer. Here is an outline of the talk. First, problem statement will be introduced, followed by motivation. A UAS testing mechanism that utilizes a high-fidelity simulation environment will be discussed. Then, its development using MBSE will be presented. Finally, we will conclude. As sensors and processors become more advanced, the algorithms for unmanned autonomous system control will also become more autonomous. Treating the autonomy as a black box and evaluating its performance in simple pass-fail terms is insufficient to fully characterize its capabilities and limitations. Greater insight into how the UAS perceives its environment and makes decisions is necessary for testers and users to gain confidence and trust in using the unmanned autonomous system. The ability to predict behaviors of increasingly intelligent systems of UAS and evaluate their performance is seen as a critical test and evaluation shortfall. Because testers seldom have access to the internal algorithms of UAS, they need a tool that can provide them with insight into how unmanned autonomous system perceives its world and what behaviors it will exhibit. The first problem we want to address is how to develop such a tool. Then, the second problem to address is how to manage the system modeling complexity and maintaining traceability of design decisions made at each level of the development of the test and evaluation tool to satisfy stakeholders' needs. There are a couple of reasons behind the need to address the problems mentioned. First is because unmanned autonomous system development is driving toward increasing levels of autonomy for unmanned systems. Another is because the ability to predict the behavior and evaluate performance of increasingly intelligent systems, especially those that employ vision-based behaviors, is a current critical test and evaluation shortfall that need to be addressed. To address the first challenge, we propose, in this paper, to use a high-fidelity simulation environment. This can significantly aid in the evaluation of unmanned autonomous system behaviors and their perception mechanisms. Such a high-fidelity simulator enables the testees to safely conduct a wide variety of mission scenarios to test an autonomous system by providing truth data to compare with the system perceptions. Figure shows the proposed system architecture, which consists of system under test, simulation environment, behavior estimator, comparator, and tester's interface, and their relations. The testers need the ability to peer into the autonomy process to see where the autonomous system's decision-making diverged from what was expected. Further, by modeling the system's behavior, testers will better be able to predict such occurrences in other scenarios. One can address these needs through the development of a methodology to monitor the system under test behaviors, infer internal states of reasoning, and predict system performance across a wide range of scenarios. The test tool created with this methodology will enhance current simulation-based testing techniques. However, it is challenging to manage the system modeling complexity and maintaining traceability of design decisions made at each level of the development of such systems to satisfy stakeholders' needs. With this regard, to address the second challenge, we followed model-based systems methodology and use systems modeling language to establish a systematic framework for designing a test and evaluation tool for unmanned autonomous systems. Model-based systems engineering has been applied to several applications, such as CubeSat, robotic systems, and aircraft systems. Development of a UAS test and evaluation tool using MBSE. Figure shows the activities we will follow for designing the tool and to systematically transform the stakeholders' needs to design requirements, which enables the integration of design, development, verification, and validation. We split the process into two. The first part, which consists of test and evaluation mission analysis process, stakeholder needs and requirements definition process, system requirements definition process, and architecture definition process, will be discussed in this paper. The second part, which has design, implementation, verification, and operation processes, will be our follow-up future work. First is test and evaluation mission analysis process. It includes preparation for mission analysis, problem definition, solution space, evaluation, and management of the mission analysis. The main goal is to test and evaluate an intelligent autonomous system from a cognitive perspective and correlate its internal processes with observed behaviors. It should satisfy the stakeholders' needs at different levels, which consists of a simulation environment and interface requirements. Therefore, testing in a high-fidelity simulation environment is the solution. It holds valid under given assumptions and constraints. The assumptions are: 1. System under test characteristics fed to the predictive technology are accurate or not largely altered due to noise. 2. The simulation tool can provide an immersive environment with realistic sensor stimuli for triggering the behaviors of intelligent autonomous systems. And 3. Estimation technology needs are achievable. The constraints, on the other hand, are: the predictive technology needs to be trained before use and the system under test needs to be one of the types of UAS that predictive technology is trained on, which is defined on maximum weight, nominal operating altitude, and speed parameters, to mention some. Goals, objectives, and needs are shown here. In the paper, we also present test operation sequence and testers' involvement use case diagrams. Next is stakeholder needs and requirements definition process. Figure summarizes test and evaluation requirements and stakeholders' needs and their refinement using requirement diagram. Figure here shows the system requirements using a requirement diagram. The main system requirements are: first, the simulation environment shall simulate a wide variety of mission scenarios for the system under test to operate on. Second, the prediction tool shall observe and classify external behaviors of the SUT and predict the internal processes by correlating with the external behaviors. Third, the system shall show whether UAS passes the test. Other detail requirements on state estimator, perception estimator, and data requirements are presented in the paper. They are not discussed here for brevity of the talk. The last part of the system design in Part 1 is architecture definition process. Its purpose is to generate system architecture alternatives that meet system requirements. Figure presents the structure of test and evaluation system architecture and relation between the components using block definition diagram. The system consists of a system under test, simulation environment, and prediction tool. The prediction tool comprises predictive technologies 1 and 2 and testers interface. The simulation environment provides a scene for the system under test to operate on and for the tester's display as a ground truth. Technology 1 predicts the external behaviors of the UAS, such as the state it is operating, from communication, message between the SUT and ground operator. Technology 2 inputs all information and predicts the internal processing of the UAS to hint the tester as to why UAS performs a particular action. Both external and internal predictions, along with the scene, will be displayed on the tester's interface. Note that we didn't discuss the details of technologies in this paper. They will be presented in more detail in our next work, which includes design, implementation, verification, and operation of the test and evaluation tool. In conclusion, in this paper, we proposed UAS testing in a high-fidelity simulation environment to address UAS test and evaluation shortfall and managed its development using model-based systems engineering. In particular, we transformed stakeholders' needs into requirements. This covers processes of mission analysis and definitions of needs, requirements, and architecture. The authors would like to acknowledge the support from the National Science Foundation under the award number 1832110, Air Force Research Laboratory and OSD under agreement number FA8750-15-2-0116. The views and conclusions contained herein are those of the authors and should not be interpreted as necessarily representing the official policies or endorsements, either expressed or implied, of NSF, AFRL, OSD, or the U.S. government. Thank you. If you have any questions, suggestions, or comments, please send us an email.